Hi, I'm Tom, and I'm here to talk to you about my megafave number, which is my favorite number, at least currently, greater than a million. My megafave number is 1,235,520. This number is related to this rectangular prism, which has dimensions 240 by 117 by 44. In particular, it's the volume of this rectangular prism. So you might be wondering, why have I chosen this seemingly random rectangular prism to create my favorite mega number? Well, it turns out that this rectangular prism is known as an Euler brick, or a rational cuboid. As we've seen, it already has integer edge length, 240 by 117 by 44. But maybe more interesting is if we compute the lengths of the face diagonals, 244, 267, and 125, all of the face diagonals are also integers. And that's what makes this an Euler brick. And it turns out that the one I've shown you is the smallest Euler brick. So you might wonder why I didn't choose the volume of the largest Euler brick for my megafave number. Well, for that to be the case, there would have to be such a largest Euler brick, and it turns out that there are infinitely many such Euler bricks, so there is no largest one. So that might prompt you to wonder how you would prove that there are infinitely many Euler bricks. And I'm going to walk you through one parameterization known as Saunders parameterization that will create an infinite family, though it won't create all of them. To do this, we start with the simple Pythagorean triples. And the Pythagorean triples have the form m squared plus n squared on the hypotenuse, m squared minus n squared on the leg, and 2mn on another leg. Given this parameterization for a Pythagorean triple, we can plug in appropriate values, and we can get two related but different Pythagorean triples. Notice that the brown triangle has this leg the same length as this leg. That's because we scaled up by u here, we scaled up by v here, and we plugged in different values here. So now that we have two Pythagorean triples that match along one edge, we just need one third one that will match along the other edges. To find this third Pythagorean triple, we're going to use a visual technique known as Garfield's trapezoid. And we're going to prove the lemma that says if you're given a Pythagorean triple u, v, and w, that means w squared is u squared plus v squared, then you're going to get a much more complicated Pythagorean triple, which we've listed right here. V times the absolute value of 3u squared minus v squared, u times the absolute value of 3v squared minus u squared, and w cubed. Here's how this works. This is a picture of Garfield's trapezoid. You can see that the white triangle that's not shaded comes from the Pythagorean triple u squared plus v squared equals w squared. And then we scale up by the appropriate value. The other two triangles that are blue are similar triangles, and they are related to the other parameterizations that we did. If you look at the Garfield's triangle trapezoid, you'll see that there's a missing triangle to form a rectangle. And when you fill in that right triangle, you get the right triangle that we're looking for, which has the Pythagorean triple that we're looking for. You can also verify this algebraically, but the visual is supposed to imply that this is the case. Now we're going to take our three Pythagorean triples that we found, the one from the red triangle right there, and the other two that came from scaling up, which were the green and the tan triangles, and it turns out that you can check, remembering that w squared equals u squared plus v squared, that they glue together very nicely in this form, and you can fold up the sides of those box to form a Euler brick. So if we start with the simplest Pythagorean triple, which is the 3, 4, 5, then we get our smallest Euler brick, which has volume 1,235,520, and that's my megafave number. Before I leave you, I'll leave you with one more question to wonder about. As we've seen, the Euler brick has integer edge lengths and integer face diagonals. You might be wondering, is it possible to find an Euler brick where the interior diagonal is also an integer length? I'll let you think about that one on your own.